So maybe you've heard of NumPy's quad function, and if you haven't, well, then there's a video from yours truly going over this function. What quad allows you to do is you define a function f of x, and you can integrate that function over some domain numerically to solve integrals that you can't normally solve by hand. And this is great, but then you get to real life practice and you find, okay, I need to integrate this function tens of thousands of times. And you might say, well, why do I need to do that? Well, in practice, maybe there's a parameter. This function f of x has a scaling factor, maybe e to the negative ax squared, for example, and you want to solve this integral for many different values of a. So you have a couple choices. You can loop over the quad function and spend lots and lots of time evaluating integrals, or you can use the quadvec function, which we'll get into in this video. Be sure to like, subscribe, join the Discord server. There's a link in the description. All the code is in the description as well, and enjoy. So for packages, we have NumPy and Matplotlib as standard. From SciPy's integration library, we're going to import both quadvec and quad. We'll compare using quadvec to evaluate many integrals versus like looping over quad. You'll see that this is much faster. We'll use time to actually show that quadvec is faster, and then here's the plotting style that we'll use. So the motivation behind quadvec is sort of as follows. This is one way it can be used. I think this is probably the main way it's used. But suppose you have a function f of x, and then I have a semicolon here, a. And so x is a variable that you want to integrate over, but a is like a particular parameter of a problem that you're solving. For example, a might be like the length of the rod that you're integrating over. Maybe it's the charge of a sphere. You know, it could be the voltage of some device, but it's a parameter. And the idea is that you want to compute an integral from x1 to x2 of f of x a dx, but for many different values of a. And this is sort of common if you want to consider, well, maybe the integral of f of x is something you want to know about your system. And you want to say, well, what happens when I change a? How does the integral change? And so for doing this, there's sort of two options. You could use the quad function and loop over, just make an array of a values and loop over all the values of a. And I sort of have a list here that you can see. This would be sort of one way to do it. You say quad f, you integrate from x1 to x2. These are the arguments for ai and a. By the way, check out my video on the quad function. That's the basic integration function. I'll put a link above. But the alternative, if you want to have many different values of a that you want to evaluate this integral for, is to use quadvec. And so this is how we'll do it. So here's 10,000 different values of a between 1 to 2. And we're going to define f of x a as this function here. It's just e to the negative a times x squared, right? And so we can integrate this from -1 to 3. And what we'll do, it's very simple to use. You just say quadvec. I pass in the function. Integrating x, that's the first argument from -1 to 3. And the arguments, which is the next parameter here, a, it knows that, you know, any arguments coming after the first variable are non-integration variables. So it's going to feed in this array of a values into here. And when I run this code, you'll see that I have a separate integral for each value of a, all the way from 1.633 to 1.224. And of course, it gives the integrals and then an estimate of the error. If I just want the integrals themselves, I would index 0. And then each one of these corresponds to the integral for a particular value of a. So as you can see, it's quite easy to use, but the illuminating thing here is comparing it to looping over quad, which I feel like most people do. Quadvec isn't a very popular function. And so here's a way that we can actually compare the timing. So I'll take the time when I start running the cell. This is 10,000 integrals using quadvec for each different value of a. I'll take time 2 and I'll print the time difference. And you can see that it takes about 0.013 seconds. Whereas if I loop over quad, so here I have my array of a values, and I'm going to say I want quad. I go f from -1 to 3. My arguments are ai for ai and a. So it takes all the different values in this array a, and it passes it into this. And this is sort of a list comprehension that's going on here. And if I print this time, you can see it takes a little longer. It's 1.166 seconds. So it's about 100 times faster to use quadvec when you have problems where you have many different parameters in your integration problem. The question, of course, is, well, what if there's more than one parameter? And it gets a little bit complicated. Suppose we want to consider different combinations of a and b in this function here. F of x a b is e to the negative a x minus b squared. So this would be a function you want to integrate over. And so you could define it like this, f of x a b, and this is what it returns, e to the negative a x minus b squared. And so suppose you have these values that you want to consider as follows. So I have A as this array here, 1 to 19, it's just like this. And then B, maybe I want to consider more values, 0 to 5, 100 different steps there. And so my A and B are different. And I want to consider all different combinations of A and B. Now, if you've seen my mesh grid video, you know exactly how to combine all different combinations of two different arrays. And so what I do is I make a mesh grid. AVBV is np.meshgrid AB. And I can look at these arrays here. If you're confused what these mean, check out my mesh grid video. And what you can do is you can actually feed in a mesh grid to the quadvec function. And so it will take the parameter space of A on one axis and B on the other axis. It will evaluate the integral for all different possible combinations of A and B in the range A goes from 1 to 20 and B goes from 0 to 5. And of course, these are discrete steps here. And so I feed in, I just call the function as I would normally. I feed in F. X gets integrated from -1 to 3. And my A and B here are now mesh grids. So I have a 2D array returned that's, sort of an A, B space, right? A and B are now the different parameters of this problem. And so I can solve this integral. And of course, my integral, because AV and BV are 2D arrays themselves, my integral will be a 2D array. And I can use P color mesh to plot the integral in A, B space, right? A on one axis, B on the other axis, which are the different combinations I'm considering. And so I plot that here, and you can see, well, here's A on one axis, B on the other axis, and you choose a particular value of A and B, and the color tells you what the result of the integral is. So this is sort of how you would do multiple parameters using the quadvec. And of course, there's a lot of different integrals that are taken here, one for each value of A and B, but it's very efficient using the quadvec function. Finally, there's another interesting thing that I sort of wanted to consider here. This probably isn't so talked about in the documentation, but the question is, what if the integration bounds depend on A? For example, you want to integrate from -a to a of e to the negative x over a squared dx, right? So you want to do that for many different values of A. Well, the best way to do this, and this is a bit of a trick, is to include the bounds, right? -a to a, inside the function. So here's my f of x a, and this might look confusing right now. But what it does is, well, if I set, for example, x equal to 2, and I say x is less than or equal to 1, that's false. And if I multiply this, say, times 5, I get 0, right? And so you can multiply this by a number, and it sets it to 0 if this condition is not true. So what this means here in my f of x a is that if x is not greater than or equal to -a, and less than or equal to a, which is precisely the bounds of integration, then this whole thing multiplies equal to 0. This is a trick that we're using here. And then rather than integrating from -a to a, here's a bunch of different values of a, by the way, 1 to 20, we integrate from -infinity to infinity. And by incorporating the bounds of the function inside the function, we can then evaluate this integral for many different values of a. And so I define my function, I define a here, and I can perform the integral for many different values of a, integrating from -infinity to infinity each time, but remembering that this takes into account the bounds, so the function is automatically 0 when x is less than -a or greater than a. So it effectively takes this integral. If you enjoyed yourself watching this video, be sure to like and subscribe. I'm bound to make mistakes when I make videos. If you caught a mistake that I made, please leave a comment on the video. I'll make sure to correct it. Check out the link to the Discord server as well, and I'll see you next time.